This is Project 5 Video 3, the one in which we do the documentation and finishing touches. So here you have to explain what phi does. It calculates the electric potential due to a pair of charges, one at 0, 0, comma, 0.5, positive charge, positive 50 nanocoulombs at that location, and then the other one at 0, 0, minus 0.5 meters, and it having charge minus 5 nanocoulombs. But in your own words. And then I'm always afraid I'll forget to put my name on there, so by Jeffrey Schneck. Don't forget that. You guys have been perfect at that so far. And then a little space there, and input variables. Okay, this is kind of important on this one because you can't tell just by looking at it. R is an array. Call it X, Y, Z of the position of the coordinates of the point at which we wish to find the electric potential, or the value of the electric potential. Hope you can find your own words to write that in. There was just one, so I think I'll put it down that way. And then percent output variable. There is just one. Percent and 5L is the value of the electric potential at X, Y, Z, where I introduce X, Y, Z up here, so I think I'm okay. So this represents a vector plus Q at zero, 0.05 meters. Yeah, I think I'll leave that. I think people can see what that is. It's coordinates of a point above the z-axis, and R minus A is going to be the difference between those two vectors. We can think of this as vector, position vector for the positive charge and I'll add a little bit to that. Minus A is position vector for the negative charge. Alright, this is obviously Coulomb constant. I'm going to put this down. Yeah, to me, things are a little less self-explanatory in this code than they have been in some of my other code. Distance of point P and I'm gonna calcs in my case, at least based on the comment that I have below, includes point P. So when I talk about point P, the point at which, so I've defined P twice, once up here in the description and once in the in there. Distance of point P from plus charge, so the positively charged particle, and then Control C, Control V from the minus charge. And then I think we're okay. I think I'll put that in quotes. Oh boy, I want to do the same thing up there then. Control C, Control V, and then quote minus quote. Alright, then attribution. Story here. Alright. The whole story about, you know, I did this on my own, then I looked at the video for that, or I just copied it straight out of all the videos because I didn't have time, whatever the true story is. But the whole story. I think I've actually got that one covered then. So stuff that wasn't clear, I think I've cleared up, and then tell the story about you know, what help you used where, how you arrived at the whole thing. So that was the easy one. This one. For my purposes, I want to define point P there. Then it's already been defined by Jeffrey. Oh, good, I remembered. You guys have been perfect. I hate to be the one that blows that. And then percent input variable. So R is array of coordinates of point P. evec is array of components of electric field vec at point P. Then this time I think it is self-explanatory. It, as the reader starts reading this, it might not make sense, but then they get to here and they say, oh, I see. They're using minus delta phi divided by delta x, and then you see yeah. Here's the idea. When x changes by an amount step, how much does phi change? Well, if it goes from r plus a half a step to r minus, from r minus a half a step to r plus a half a step, that that represents a change in where we're evaluating the phi of step, the whole dx. And so we're getting delta phi divided by delta x there, with changing nothing but the x part, where we're evaluating phi, and then changing nothing but the y part divided by dy. So the step represents dy there. So yeah, by the time you get down to here, it's pretty obvious what was going on up here. This is a half of dx, and it's a vector. Just I think it's perfect. I think it's self-explanatory what's going on here. I mean, we gotta say that we're calculating E using the idea that E is the negative of the gradient. So we got a lot of explanation up there, and then here it's obvious. It's pretty clear if you know what you're supposed to be doing, that's what's going on in this step, and then that makes those clear. So attribution. In my case, I didn't wind up looking anything up on the internet for this. I remembered about the norm, and I had to play around with it, and I wasn't sure how to deal with the idea that this is a vector. Do I have to tell it somewhere in here that it's a vector? And it's no. I just start using it as if it were a vector, and not a vector, an array, the array of 3 values. But the user has to be smart enough to pass it as an array, to give E an array of 3 values. And attribution goes here. Tell the story of how you came up with this code. Hopefully you did it all on your own, but I did most of it on my own, and I consulted the video for some ideas. There's so many different ways of doing this. I want to one of them that I was talking to you guys about, there's remember RVec? It's got 1, 2, and 3 from when I was playing around with that in the very first video. RVec of 1 means the first element of the array RVec. It's a 1. Oh, that's kind of a little bit hokey. Let's make RVec equals 5, 11, 14. Then RVec of 1. I didn't like the other one because RVec of 1 was 1, RVec of 2 was 2, RVec of 3 was 3. You wouldn't see the general idea, but it's the first element stored in RVec, and then RVec of 2 is the second element stored in it, which should be an 11, and RVec of 3 is the third element stored in RVec. So for instance, instead of the norm, we could go rmag equals square root of r vec of 1 squared plus, let's see if I can copy and paste faster than I can type it. Never know whether it's using more time or less time, but this would be 3 and this would be 2. And yeah, if I take on the calculator, well, that's the norm. Let's go make sure I get the same answer. Norm of RVEC. Get the same exact answer. So you can calculate the magnitude of a vector, the distance r that we needed doing that. An awful lot of things that you could do on your own, quite different from the way I coded it up, but the way I coded it up does seem to be working. Alright, then make sure they're still working. I guess we really just need to make sure E is working. Let's do an R at the new RVEC, should be the smallest one, or E at the new RVEC. I'm going to EVEC. Oh, I want to see what happens if I just do it without assigning it to anything. I think I just get like the first element of the answer. So of RVEC, it says answer equals and then just one value. So I'm wrong. This is what it returns. All 3 values. We're way out there. We're what was it? 5, 11, 14 meters away from these 2 tiny little charged particles that are very near the origin, each a half a centimeter away from the origin. So we would expect the electric field to be weak, and we're getting that. And I think that's probably, it looks like it's still working. So it's not spitting out anything that it's not supposed to spit out. To me it looks a little bit neater if I assign it to something. But no, and it just says EVEC is equal to that instead of answer is equal to that, so it's not that much neater. But take one last look at these guys, make sure. Oh, I know, I want to go through my checklist. Better go through the checklist real quick. So, in case I forgot something, a complete algebraic solution, including any relevant diagrams. I did have some diagrams, thank goodness. For each function, outline of the steps, I remember doing that. As for the program part, reasonable attempt for each one. Got to be one or more .m files. I get 2 .m files. This one has to be 2 .m files. 1 point for a program that works. I think it works. I haven't actually absolutely proved it, but seems it passed the test that I could give it kind of quickly without subbing out the whole problem by hand, which I didn't feel like doing. It might not be a bad idea for you to do that. Be interesting to calculate E by hand and compare it with what this gives you, because this is an approximation. I think you'll find that it's a really good approximation. Does what it's supposed to do and prints nothing extra to the command window. See, I only had to run E to check that, because E cos phi, so if phi was printing something to the screen every time it ran, we'd get a pile of stuff printed to the screen. But nope, all we're getting is the final output of E. So not printing any extra stuff to the command window, so we're good for that. Documentation, final touches. Have your name. I did remember to do that. Got my name in every single one. Got to be documented for each function. Statement starting on the first line, setting what the function does. Okay, I didn't actually do that, but I told you to do it, like right there and right there. Oops, right there. Another set of comments, providing a list of the arguments of the function, the input variables. So the only argument is R, And to me, it's more important than in the usual case, somebody coming across this function wanting to use it, figure out what R is. So I could have named it R array, which might have helped, but or R vec, but it's clarified down here. And I remember doing input and output for both of them, so I think I'm okay there. Same thing for output. Did that for the case of a function that includes segments that are not self-explanatory. I did not think that the phi function was particularly self-explanatory. So put some comments in there. It's just a matter of, what are these things that we're calculating. So I got that. It doesn't do any graphs, so I don't have to worry about graphs. You must provide attribution. In my case, I would have to say no outside resources were used. So I wrote it from scratch in both cases. If you looked at my video, that's not something you want to do. You got to at least say, tell me how you use the video. Remember, don't just say referred to videos. Okay, so as far as I'm concerned, that does it for the whole project. That's a wrap for project 5, video number 3.